Hi, here we are discussing about a project toward the multiple constant multiplications at minimal hardware cost. Here, the multiple constant multiplications over integer is a frequent operations requiring the highly optimized hardware in the design of VLSI design. A multiplierless circuit is an efficient method for replacing costly generic multiplications with bit shift and additions. In this paper, we enhance the current optimal approach for MCM, which is based on the integer linear program. We introduce a new low-level hardware cost matrix based on the number of 1-bit adders and demonstrate that is a correlates strongly with the number of LUTs. The proposed ILP model for multiple variant of MCMs are implemented as an ECG 8th order FIR filter designs. We conduct extensive experiment to evaluate our models and propose an in-depth of analysis effect and designs matrix on synthesized hardware and analyzes the area, delay and power. Now we can verify the base paper. So this base paper is fully designed for the multiple constant multiplications with a minimal hardware cost. For minimal hardware cost, what we have do means we are developed a new novelty based architectures for each and every coefficients of the FIR filter design. So that is called a multiple constant multiplications. Okay, so this paper purely they are not used any multipliers. Okay, instead of the multipliers they are used shift registers and adders. Okay, so based upon the shift registers and adders we can reduce the multipliers. Okay, so here the multipliers means it will take a more number of logic sizes compared to the shifting operations and addition. Why? Because if you are taken a 8 cross 8 bit multiplications mean it will take a 64 partial product. This much 64 partial product we need to use a number of full adders. Okay, and we need to reduce a number of partial product with a number of stages. Okay, next this multiplier 8 cross 8 multiplier provide a 16-bit output. Okay, so based upon the 16-bit output we need to use after the multiplication process addition also we need to use a 16-bit adder. Okay, but here we can truncate all the thing. Okay, so examples if we use shift and addition based constant multiplications part, we are not need a 16-bit additions in the final stage. Okay, we can use a 8-bit addition, and internal architecture of this process also we will get a better results. Okay, so here the figure 1 it will be shown the examples of the multiplications. Okay, so constant multiplications, that is a 51x and 49x. Okay, so here figure 1b it will be showing 49x plus 51x. Okay, so we can do the different number of architectures. Okay, so here the A architectures equal to AD3 and B architecture equal to AD2. Okay, so here you can analyze it. So here you can analyze the number of additions and number of shifting operations. Okay, so here they are using 3 shifting method, 2 3 shifting method. Okay, and 1 shifting method here. Okay, so here they are used 2 4 shifting method and 1 shifting method here. Okay, here in the FIR filter we have different level of architectures. Okay, direct form, transpose forms and folded form FIR filter. Okay, so we can use this type of topologies in every form of FIR filter design. Okay, so here the proposed method they are used the truncated form. So here this is a section 6, the truncated MCM. Okay, so here truncated MCM means they are truncated the number of bit zeros. Okay, so LSB bit truncated. Okay, so they are padding with the number of bit zeros. As per that they will get a output as a truncated method. Okay, so truncated it's a approximate method, it's not accurate method. So in most of the method approximate additions is enough compared to the arithmetic accurate operations. Okay, why? Because here approximate operations will take a less number of logic sizes compared to the accurate. Okay, that's why we focus for approximate values. So here the truncation is one of the approximation technique. So here we will use a number of shifting padding with zeros, and we will truncated the LSB part. Okay, so based upon that, this architecture logic sizes will automatically reduced. Okay, so this is the proposed idea of this paper. So here what we have done in the proposed idea means, we have done two methods. One is a normal addition based MCM using ECG-FR filter. Okay, so this type of method. Okay, and the second one is we have used a truncated addition with the XOR mux full adders. So here addition part they are used some full adders, right? So that full adder we have used with the XOR mux concept. Okay, so here that multiplication also we are used in the ECG 8th order FR filter design. Okay, so here the coefficients means we will get number of coefficients. Okay, so 1, 5, 15, 25, 30, 9, 15. Okay, so example, this architectures we can show how to design the architecture. Okay, so this is a reference architecture for 15x1 plus 5x2. Okay, so based upon this architecture design we will create a novelty in this FR filter design. Okay, as per the novelty architecture we have developed in the code. Okay, so here 8th order means we need 8 coefficients, so 8 number of multiplications concept we need to develop it. Okay, so here this is a Verla HDL code. Okay, so here we are given as a ECG input and at the top model, and this is the multiplications part. Okay, and this is a proposed level of the coding. Okay, and this is a simulation report for the existing method. So existing method means normal FR filter design. Okay, so here you can analyze it, the input and output. Okay, so ECG input and ECG output. So here we are used MIT BIS dataset. Okay, and this is a truncated form. So this is the input and this is output. So internal architectures we have used truncated method. Okay, so here you can analyze it anywhere the ECG signals will be present. Okay, so here the x1, x2, x3 means it will come up with 4-bit concept. So here mostly the 4-bit we are used here. Okay, the balance 4-bit we are truncated in the architecture. Okay, so we will show this part in a schematic level. Okay, we can't possible to show all the codes in the video file. Okay, so this is the existing synthesized report. So here you can analyze the number of slice registers, LUTs and occupied slices and airbase. Okay, so here RTL schematic we can verify it. Okay, so here you can analyze the RTL schematic. So the filter input given directly to the number of flip-flops. Okay, so here this flip-flops sample the value and it will given to the MCM. Okay, so this is a MCM architecture for 1x plus a 5x. Okay, and this is the architecture for 15x plus 25x, and this is architecture for 30x plus 9x. Okay, and this is architecture for 15x plus 5x. Okay, so this architectures we have developed it. After that the final additions we are done here, and finally we are taken as the output. Okay, so this architectures we are not used any multipliers. Okay, only addition part only we have used it. So here all the RCA ripple carry adder will have used in a 8-bit level only. Okay, not in 4-bit level, not truncated method applied here. Okay, so here this RCA it will support with the full adders. Okay, after that we have used a proposed synthesized method. So here you can analyze the number of slice registers, LUT, occupied slices, IO base. Okay, and you can analyze the RL schematic. So here the internal architectures, 1x cross 5x and 15x cross 25x, 30x cross 9x. Okay, so here you can verify it. Okay, so here we have used 4-bit only. Okay, and in the normal addition method we have used RCA 8. Okay, so this is a 8-bit RCA, but here we have used only 4-bit RCA. Okay, so each bit will consider as a 4-bit, and internal architecture of this RCA we have used as a XOR mux full adder design. Okay, so it will come with the XOR gate and multiplexer design. Okay, but in the existing we have used as a 2 half adder based architectures. Okay, so based upon this 2 level of comparisons, we have certain values in the table. Okay, so here this is a proposed output parameter value. Okay, so this is analysis chart. Okay, and we have written abstract document for this project. Okay, so here you can analyze a base paper abstract, improvement of the project, proposed title, proposed abstract, exit system, disadvantages and proposed system, advantages and related notes, and finally come up with the literature survey and references. Okay, thank you.